Fog rolls through a gaping limestone chasm, hiding the raging river 2,000 feet below in impenetrable shadow. An ironworker clings to a vibrating steel wire, suspended directly over nothingness as canyon gales slam into his chest.
Suspended half a mile above the abyss, this platform offers a unique perspective on the raw power and immense depth of this landscape.
For centuries, the mountainous province of Guizhou was carved into isolated pockets by thousands of towering, jagged limestone canyons. Crossing from one sheer cliff face to another meant a grueling, multi-hour journey down winding, treacherous mountain switchbacks. Families were separated by geography so violent that local legend claimed even birds struggled to cross the chasms. Then, engineers proposed something that sounded less like civil engineering and more like absolute madness. They would build a 4-lane highway suspension bridge straight across the deepest gorge in the region. The deck would hang higher than the tip of the Eiffel Tower, exposed to unpredictable weather extremes. Critics warned the wind shears would rip any structure apart before construction could even finish. But the nation's infrastructure planners refused to back down from the staggering vertical abyss.
The geology on the south side is stable enough for the anchor points.
This is the story of how engineers conquered the vertical void to build the Beipanjiang Bridge, Duje, a marvel spanning over 2,000 feet above the roaring Beipan River. To understand the sheer scale of the challenge, you have to look closely at the rugged landscape of southwestern China. Over 90% of the province is covered by steep mountains and fragile, hollow limestone karsts. Rainwater carving through stone over millions of years has left the region riddled with underground caves and unstable cliffs. They said nobody could anchor a heavy structure to rock that crumbles like dry chalk. Building standard roads here meant blasting millions of tons of rock while hanging off vertical precipices. Heavy trucks carrying vital goods spent hours burning fuel just to navigate a few miles of horizontal distance. Economic growth slowed to a crawl because the terrain acted like an impenetrable fortress wall. The central government realized that traditional transport networks could never bridge these immense natural divides. A massive connectivity push was launched, demanding highways that could slice straight through the mountainous barriers. But one specific river valley presented a vertical obstacle unlike anything attempted in modern civil history. A sheer drop of over 2,000 feet separated two vertical rock faces across a roaring river. No traditional scaffolding could reach from the valley floor. It would be taller than the world's tallest skyscrapers. Any construction equipment placed below would be entirely at the mercy of sudden, deadly flash floods. Engineers faced an unforgiving blank canvas where every single rule of standard bridge building instantly failed. The solution required throwing out conventional blueprints and inventing an entirely new method of aerial deployment. If you cannot build upward from the bottom, you must build outward from the top down. Designers proposed a colossal suspension bridge anchored directly into the solid interior of the cliff faces. Instead of concrete pillars touching the ground, massive steel cables would bear the entire weight of traffic. But first, the team had to figure out how to get a starter line across 2,000 feet of empty air. How do you bridge a chasm when you cannot even walk across it? Traditional methods of sending boats or workers across were completely impossible given the lethal drop. Engineers turned to specialized rocket-propelled pilot lines to shoot the first thin guide wire across the gorge. A high-powered compressed air launcher fired a lightweight tether from one cliff face directly to the other. Once the initial thread made contact, heavier steel cables were pulled across one by one in sequence. This invisible spider web of wire became the backbone for hoisting heavier machinery across the abyss. A precarious aerial highway was born, suspended entirely on faith, physics, and high tensile steel. Before a single ton of steel was ordered, geologists mapped every crack and fissure in the limestone cliffs. Laser scanners revealed internal voids within the rock that could threaten the anchor tunnel stability. Engineers injected thousands of gallons of liquid concrete deep into the mountain to seal hidden faults.
The scale of the megastructure pulse is unprecedented. Engineers had to bore directly into this sheer cliff face to secure the foundation against the elements below.
Wind tunnel testing replicated the erratic canyon gales using a massive physical model of the bridge deck. Designers discovered that flat, solid road decks acted like giant airplane wings, catching destructive, uplifting winds. The solution was an open truss steel deck design, featuring narrow aerodynamic slots to let air flow freely through. We weren't just designing a road, we were building an aircraft wing designed to stay completely still. Every component was modeled digitally to withstand extreme seismic shaking and thermal expansion across seasonal temperature swings. With the digital blueprints verified, the multi-million-dollar gamble moved from computer screens into the brutal reality of the canyon. High above the rushing river, ironworkers step out onto narrow temporary catwalks, swaying violently in the mist. Massive tower cranes anchor to the sheer vertical stone, lifting multi-ton steel segments piece by painstaking piece. Right now, workers are bolting together the main suspension towers that stand taller than a 40-story skyscraper. Each tower must align with millimeter precision. Even a tiny fraction of an inch error multiplies across the span. The cable spinning process begins, pulling thousands of individual galvanized steel wires across the 2,000-foot void. A high-speed wheel races back and forth along the guide cable, laying down strand after parallel strand. The air fills with the constant, high-pitched metallic whine of steel wire sliding under immense mechanical tension.
Workers squeeze the loose bundles together into massive main cables thicker than a grown man's torso. Heavy hydraulic presses clamp steel collars around the bundles, locking the titanic weight-bearing capacity into place. Suspended vertical wire ropes drop downward from the main cables, forming a rhythmic grid of steel hangers. Below these ropes, massive steel deck segments roll out from cliffside assembly yards on heavy transport rails. A specialized overhead crane hoists each massive deck section up from the abyss like a fishing line. Workers weld the floating segments together one by one, sealing the gap above the churning river below. The structure gains weight by the hour, shifting and settling as millions of pounds of steel lock together. Summer temperatures bake the metal framework, forcing engineers to calculate thermal expansion in real time. If we miscalculate the heat expansion by a millimeter, the entire deck warps under the midday sun. Finally, the last central gap closes, uniting the two opposing mountain cliffs in a continuous ribbon of steel. To understand why this bridge does not collapse, you have to look at how weight is distributed. Every car and truck crossing the deck transfers its load down through the vertical steel hanger ropes. Those ropes feed the weight directly into the two massive main cables arching gracefully overhead. The cables carry that titanic pressure outward, pulling against towering concrete pylons anchored on each side. From the pylons, the forces plunge deep underground into massive anchor chambers tunneled inside solid rock. The mountain itself acts as a giant clamp, absorbing the pull of thousands of tons of suspension force. It is essentially a giant bow and arrow where the mountain holds the string under permanent tension. Meanwhile, the open truss deck structure allows high winds to pass straight through without creating dangerous twisting motions.
Hydraulic shock absorbers at the expansion joints cushion the bridge against sudden temperature drops and ground tremors. Every single physical force is counterbalanced, neutralized, or safely channeled directly into the Earth's ancient bedrock. Nothing is left to chance. Sensors monitor structural stress points 24 hours a day across the network. The bridge functions not as a rigid wall, but as a living, flexible machine designed to breathe with nature. But theoretical physics and computer models mean nothing until nature decides to throw its absolute worst at the structure.
High above the Beipanjiang gorge, this is the pulse of the megastructure, a marvel of modern engineering, defying gravity itself.
Winds howling at nearly hurricane speeds slam sideways into the passing traffic, testing the aerodynamic truss design. The entire asphalt surface is vibrating, but the steel skeleton absorbs every shock wave without twisting. Sensors flash green as structural dampers shift automatically to counteract the violent atmospheric pressure changes outside. Heavy rain cascades off the bridge deck edges, plunging 2,000 feet straight down into the misty void. Down below on the river surface, violent cross currents toss debris, while the highway above remains completely stable. Drivers cross the vast chasm in mere seconds, completely unaware of the titanic aerodynamic forces raging around them. The structure passes its ultimate meteorological trial with absolute precision, proving its design worth to the world.
This bridge represents the culmination of years of work. It stands as a testament to what's possible when we dare to build the impossible.
What was once considered an impossible barrier has been tamed into a routine morning commute. The opening of the Beipanjiang Bridge, Duja, instantly shattered decades of geographic isolation for rural communities. A treacherous journey that once took more than 4 hours now takes less than 60 seconds. Local farmers can transport fresh produce to major city markets before sunrise, transforming the regional economy. Tourism surges as travelers from across the globe flock to marvel at the engineering masterclass hanging in clouds. The bridge claimed a rightful place in history as one of the highest suspension structures ever built by humanity. It stands alongside modern engineering giants like the Golden Gate and the Miao Viaduct in global acclaim. We proved that no canyon is too deep and no mountain is too steep when human ingenuity takes over. This monumental achievement serves as a blueprint for conquering extreme geography anywhere else on Earth. It reminds us that our greatest physical barriers are only temporary boundaries waiting for the right idea. High above the misty river, traffic flows smoothly through the endless expanse of blue sky. Where nature once drew an impassable line, humanity simply built a road across the clouds.